A particle is projected horizontally from the top of a cliff at 20 meters per second. It lands in the sea 3 seconds later. We want to find the height of the cliff. Since we're finding the height of the cliff, we're interested in vertical motion. We can call the height of the cliff h. If we collect the information we know, we can use suvat because the only acceleration is gravity, and this is constant acceleration. Therefore, we're going to use the constant acceleration formulae. Remember, gravity acts vertically downwards, and we're taking it to be 9.8 meters per second squared. If we take downwards as positive, then the acceleration, being downwards, will be positive. The initial projection is all horizontal, and therefore the vertical component of initial velocity is 0. S is the height which we're trying to find. We don't know the final velocity. We know the acceleration is 9.8 meters per second squared, positive since we took downwards to be positive, and the time taken is 3 seconds. If we look at the quantities involved, we can see that we can use S equals ut plus a half at squared. The height is equal to 0 times t, which is just 0, and a half times the acceleration times the time squared. And this comes to 44.1 meters. So the cliff is 44.1 meters high. We want to know how far from the base of the cliff the particle lands. This is purely horizontal distance, and therefore we only need to consider horizontal motion. Gravity we know is vertical, so horizontally there is no acceleration. We only have to consider s, u and t, know a because there's no acceleration, and since there is no acceleration, the velocity will not change, so we don't need v. Let's call the horizontal distance d. We know the speed is 20 meters per second, and the time is 3 seconds. We just use s equals ut, distance equals speed times time, and this is 20 times 3, which is 60 meters. We want to know the speed of the particle when it hits the sea. Here is the particle landing in the sea. It has a vertical component of velocity which we don't know, and a horizontal component which we know won't change, and therefore is 20 meters per second. To work out the vertical component, we need to once again consider vertical motion. We collect the information we need using suvat. We know the initial vertical velocity is 0. The final velocity is what we like to know. The acceleration is 9.8 meters per second squared, and the time is 3 seconds. Of course, we could have used the distance is 44.1, as we found in Part A, but if we can, it's better to use information given to us, as opposed to information that we've calculated. we can use v equals u plus at. So v is going to be 0 plus 9.8 times 3. And this calculates to give 29.4 meters per second. And so we now know the vertical component. We're interested in working out the speed of the particle. We can use Pythagoras' theorem for this. The velocity goes 20 across and 29.4 down. The speed will be the length of the hypotenuse of this right-angled triangle. So v squared is 20 squared plus 29.4 squared. So v is the square root of this. And this calculates to give us 35.6 meters per second, correct to 3 significant figures. Now in part D, we want the angle between the direction of motion of the particle and the horizontal at the point where it hits the sea. This is the same triangle we had before from when the particle hits the sea. We know the horizontal component is 20 and the vertical 29.4. V shows us the direction of motion in this triangle, and the angle therefore with the horizontal is this angle. We have a right-angled triangle, and this is the opposite, and this the adjacent. Using SOH CAH TOA, we have opposite and adjacent, so we need to use the tangent. The tangent of the angle theta is going to be 29.4 divided by 20. So theta is the inverse tan, or shift tan on the calculator, of 29.4 divided by 20. And this is 55.8 degrees, correct to 3 significant figures. We now want to know how far the particle is from its starting point at the point where it lands. We know it started here, and suppose it lands here. We want the length of this line. We can form a right-angled triangle, and we've calculated the height of the cliff as 44.1 meters and this distance as 60 meters. If we call the distance d, we can use Pythagoras' theorem. So d squared is 44.1 squared plus 60 squared. And this calculates to 5,544.81, and therefore d is the square root of this and gives us 74.5 meters, correct to 3 significant figures.